Good morning, everyone. It's my great pleasure to be here today. I'm going to speak about parametric analysis of a green roof and wall mitigation scenario via ENVI-met and AHP, the effect of building height, coverage, percentage, and leaf area index. This research has been conducted by myself. I'm a researcher from the Italian National Agency for New Technology, Energy, and Sustainable Economic Development, and my former master student, Jacopo. Okay, as we all know, urban Thailand has a serious consequence on human health and illness and health-related mortality. Just less than 2 months ago, from July the 1st until July the 21st, Italy undergone almost several heat waves. And in southern Italy, we assist to an increase in mortality equal to 2%. But in some cities, for instance, my hometown, you can see in the map, because of the combination of heat wave and UHI, we witness an increase of mortality equal to 24%. Furthermore, urban Italian has also effect on the deterioration of urban uses and air quality. For instance, in Rome, where the urban Italian is equal to 3.6 degrees Celsius, there is a loss in urban ecosystem of about 14%. And of course, the increase of urban temperature entails an increase in building energy use for cooling. So it's about the most importance to mitigate urban Thailand, but not always in densely urbanized area we can find enough space to plant trees or for new parks. Therefore, in this study we evaluated the building integrated vegetation technologies applied to building which can provide enough space for cooling. In particular, we investigated the effect of green facade, living wall, and extensive green roofs. So the issue here is, okay, we have to mitigate UHI, but when urban decision makers plan how to act in cities, they need to model areas and to see which and to foresee what is going to be the mitigation potential of these actions. But this means that a lot of data are needed, and this is something that is really time consuming. And more than that, we need specific competencies. So we decide to develop some indices to foresee the mitigation potential of green roof and living wall and green facade by applying the AHP method. The AHP method is a method used for solving complex problems. Is an analytic hierarchy process, so the structure is hierarchic. So we have an objective and some criteria which influence the final objective. Okay. So there is the definition of some matrices for the criteria, one matrix for each criterion. The dimension of each matrix is equal to the number of sub-criteria. And there is a pairwise comparison. The pairwise comparison can be done by using both subjective, so qualitative judgment, and the quantitative ones. Usually, qualitative judgment are scored in order to have a kind of quantitative comparison. And for each criterion, the weights, so the importance of each criterion is defined. At the end, especially for the qualitative judgment, is checked the consistency of the weights. And at the end, we have the definition of an index by means of the weights combination. So in this specific study, the objective is to define three indices for calculating the UHI mitigation due to the application of BIVT-based scenarios. So mainly one BITV for each scenario. Mitigation potential is conducted by pairwise comparing the scenarios developed by applying the sub-criteria. In this specific case, we use quantitative pairwise comparison. So matrices have been fed with 117 ENVI-met simulation of three neighborhoods. So 99 mitigation scenarios and 18 baseline ones. The three neighborhoods are one in Rome, one in Bari, and one in Florence. All the three areas are featured by an urban density equal to 0.3, 0.4, and all the neighborhoods are in a CSA climate zone. The criteria which define the objective are defined by the literature review, and also sub-criteria has been defined. So as you can see here, these are the three built areas that have been chosen in the three cities. As you can see, for the first area in Rome, it is characterized by sparse buildings. And the second one in Bari is characterized by buildings which are aligned, mainly aligned. And the third one is characterized by buildings which are arranged around courtyards. We calculated the maximum UHI for a typical summer day in Rome, which is equal to 3.6 degrees Celsius. In Bari is equal to 3.7 degrees Celsius, and in Florence is equal to 2.5 degrees Celsius. So for our case study, the objective is the definition of UHI mitigation index. The criteria are building size expressed in meters, coverage percentage, and leaf area index. And the intensity class of sub-criteria are for building height going from 5 to 40 meters, for the coverage going from 25 to 100%, and for the leaf area index going from 1.5 to 5. So we solved all the matrices, and we found that for the extensive green roof based scenario, the weights decrease by increasing the building height. This means that the potential of extensive green roof based scenario to mitigate urban heat island decreases when the height of the buildings increases. Contrariwise, for green facade and living walls, the potential in mitigation increases by the increase of the building height. So you can see that when a building height of 20 meters is reached, there is a little residual increase in the weight, but a plateau is almost reached. Then we find also the weights related to the plant coverage. We can see that we mainly found almost linear correlation between percentage of plant coverage and potential mitigation of the three VIVTs based scenarios. And as a regard the leaf area index, we found that there is a sensible increase going from 1.5 leaf area index to 3, and then there is a further increase but to a lower extent going from 3 to 5 leaf area index. So we also developed the indexes I told you before. As you can see here, the highest weight is related to the building height. It is equal to 0.5, and the highest weight of the intensity class of the building height is equal to 5 meters. This means that mitigation scenario based on extensive green roof application has the highest decreasing potential when buildings are 5 meters high, and then their potential decrease for buildings which are higher. So we have also for green facade that the highest weight is related to the building height, and that the highest weight related to the intensity class is related to a height that goes from 20 to 40 meters. And finally, we have for living walls, we see that also in this case, the highest weight is relating to the building height, and the highest weight related to the intensity class can be found at the height of 30 meters. So, so these indexes, this mathematical expression can easily provide a mitigation potential of plants if you substitute the mean building height of the buildings, the coverage and the leaf area index. This equation will provide you an idea of the potential mitigation. In conclusion, we can say that the extensive green roof decrease their mitigation potential with the increase in building height. The best performance can be found when buildings are 5 meters high. Living walls and green facades increase their mitigation potential with the increase in building height. Plant coverage and UHI mitigation are linearly correlated. VIVTs with leaf area index equal to 3 or greater are more effective mitigating air temperature, and the leaf area index equal to 1.5 is ineffective. Predictive indices have been also validated. They showed an error equal to about 15% compared to ENVI-met simulation. This means that the indexes I showed you before can provide a quite reliable idea of the mitigation potential scenario in just few seconds. Rather than all the time that is necessary to develop a model. You can find more details about this research in the first article I report in this slide, and the same methodology has been also applied to consider the potential of mitigation plans based on different solution set. And you can see this the second article in this slide that is going to be published on renewable and sustainable energy reviews in the next few days. Thank you for your attention.
Only one question?
See, you put building height 5 meters is the optimum building. That is a scenario usually in villages. But if we go to cities, they are price capacity in most of the countries. I feel the space between the buildings, that is the street, is more important. When we go at the height of the building, that will be, say, usually we get low temperature, say, suppose 50-story building, airflow is fine and then ventilation there. So, I am feeling that there is low instead of low humidity. This width of the street should be taken into consideration. What is your view?
Okay, yeah. So, as I said, maybe I can show you. Slide.
If 5 meters is not the height even in a 2-story building. 2-story building is 6 meters plus.
Yeah.
Further height and then below.
Yeah, it's about
So it becomes 7 meters minimum.
Yeah, I mean the sub. Okay, we define this building height because we had to look at the granularity of the models. So the model is based on in this case. Sorry.
Model predicts this height.
ENVI-met. Yeah, ENVI-met. I mean, all the matrices are fed with values that are taken from ENVI-met models and simulations. That's why we decided to use 5 meters to increase the building height.
So
but
They should live in rural kind of.
Sorry.
They should live in rural kind of environment.
No. I mean, anyway, this, as I said in this slide, these results are referred to urban areas with urban density between zero point 0.3 and 0.4. If we change